Welcome back to my series all about limits. In today's episode, we will look at a new type of limit. We will see what it means for the limit as x approaches a constant of f of x to equal infinity. Like our previous episodes, we're going to start by developing an intuition for what the expressions in our equation exactly mean. So similarly to our first limit definition, we see this equals infinity, right? So that's the same idea as this unbounded increase. And if you haven't seen that first definition, I'll explain more what that unbounded increase means later. But unlike the first limit definition, we see that x is approaching some constant c. So we can think about what that means, right? X is approaching c, x is getting closer and closer to c. The distance between x and our constant c is small. And it's important to know that we're not necessarily saying whether or not x is greater than c or x is less than c. In fact, what it's saying is we're looking at values that are close in both directions. So when x is a little bit more than c, or when x is a little bit less than c. So how can we describe the distance between x and c? Well, we can say that it's the absolute value of x minus c. And we can just say that this is a small distance. Now there's one more detail about this that I want to mention. We're looking at values of x that are close to c. But remember that this is a different idea than just plugging in c into f of x, right? We're looking at the behavior of the function at values around c. So we really don't want to look necessarily at when x is equal to c. So we can just put, as a side note, x does not equal to c. But let's say we want to make this more concise, right? We're going to come up with a definition. If you've seen the last videos, you know there ends up being a bunch of words. So what happens if you plug in x, or if you plug in c into this expression right here? Right? You get c minus c, which is 0. And the absolute value of 0 is 0. So we know that this is not equal to 0. And if we're taking the absolute value of something, it's always going to be non-negative. So this will be positive anyways, and we don't want it to be equal to 0. So we can simply say that this is greater than 0. Or saying that 0 is less than x, the absolute value of x minus c. And again, all that's saying is x is close to c, but it's not necessarily equal to c. So here you can see I've drawn a graph that seems to fit our definition, right? As x is getting closer and closer to c, on both sides, we see that the value of f of x seems to just be increasing, and would just increase to infinity. So similarly to our first definition, I'm going to show a quality that this one shares. So in our first definition, we thought about choosing a value of b and then finding some cutoff for which f of a or f of x would be greater than b if x is greater than a. But instead of thinking about x being greater than a, right, we want to think about x being closer and closer to c. So what we are going to do is we're going to start with our b, and we're going to choose a width. And this width will be how wide around c? How far away from c are you allowed to get? Such that all of those values within c are greater than the b that we choose. So let's look at an example. We start with b1. Now we see, can we choose a width for c? such that whenever x is within this width of c, f of x is greater than b. So let's see here. And it looks like there's a lot of options. So perhaps we make our width within this much of c. You're allowed to be within this width of c. And why don't we name this width delta? And we'll do this on the other side, right? Because x is approaching c from both sides. So we have this width on the other side as well. And the width of these are both delta. Well, we see that we can go up here, and we can also go up here. And the x values we choose are all within this range. So we ask ourselves, if we choose an x value in this range that's within delta, right, of c, within this width, how do we compare the value of our f of x to our value of b? Well, we see that the values of f of x will always be increasing, and they'll always be, well, when x is less than c, and even though they decrease after x is greater than c, it'll always be greater than these points because we restricted it to this width. So we see, yeah, we have successfully chosen a delta such that f of x will always be greater than b when the distance between x and c is within that delta. So again, we can try this example for larger values of b. For example, why don't we look at b3? So we think, can we make a width such that whenever x is within that width of c, the value of f of x will always be greater than this b? So let's see. Can we find some sort of width, find some sort of delta that satisfies this condition? So we see, how about we set our delta to be within this width of c. And so we see from here, our f of x values go from here to here. And so we see in this range of x values that the value of f of x will always be greater than this b because we've restricted it to be within this width. And what we can see is we can keep setting b to be larger and larger. So we could set it to be b4, and we would want to make our delta even smaller. And we could keep going higher, and we could set a delta smaller, but it wouldn't matter because we could always find a delta, right? And that's what it means, right, to follow this limit. And so we can think about this as the absolute value of x minus c, which is positive, right? We're not thinking about x being exactly c. For example, in this function, there is no f of c. There's no value. We say that this is less than delta, right? Which we can see. It's within delta of c. And we say, well, given this condition for the value of x, we say, therefore, f of x is greater than b. And we can do this, right, for all b values. So now we are ready for the rigorous definition of our limit. So let's take a look. We say, for all real numbers b, we can find a positive delta, right? Delta's a distance, such that whenever 0 is less than the absolute value of x minus c, which is less than delta, then f of x will be greater than b. And I've described it in quantifiers. Here we can see the limit as x approaches c of f of x equals infinity implies that for all b, which is a real number, there exists a positive delta such that for all x, when 0 is less than the absolute value of x minus c, which is also less than delta, that implies that f of x is greater than b. And again, if you're looking at this and you're like, this is a bunch of words, we can think about this, right? That for any b, any value on that y-axis, we can always find a width that's small enough such that whenever x is within that width, f of x will be greater than b. So no matter how high a b value someone chooses, you could still choose a delta that would satisfy that condition. So there is one more thing we need to think about, especially when it comes to this type of limit definition. We need to think about, what if x only approaches c from one side? Right, in this example, we are thinking, well, x can be greater than c, x can be less than c. But you're going to find a lot of functions where either it'll approach different values depending on which side, or you might only care about values of x that are greater than c, or you might only care about values of x that are less than c. So again, if you saw my intro video, or you've already done some studying of limits, you could see that we could either put a plus sign or a negative sign above this c to imply that it's approaching from the right or approaching from the left. However, if we do this, we need to think about, how does this change the definition that we've just created? And what we see is that really what's changing is, well, where are those values of x going to go? And everything else, right, will be the same. So as you see, I erased the part where we said what x is, so we can rediscover where that should go. So first of all, let's think about what happens if we say x approaches c from the right. And again, I noted that with a plus to show that it's approaching from the right. So again, we can think about the concept of our width with c here. And if our width is delta, that means that there is some c plus that width delta. And again, going to the left side of our width will be c minus delta. So for values of x that are approaching from both sides, we would care about all of these values. But if it's only approaching from the right, then we only care about values of x that are greater than c. So we think if we're within delta of c, we're really just concerned about this range right here. So what do we know about this range? Well, we see the lowest value is c, and the highest value is c plus delta. So we say c is less than x is less than c plus delta. All right, and we can maybe simplify that a little bit. If we subtract c on all sides, that will give us 0 is less than x minus c is less than delta, which actually looks very similar to what we had before. The only difference is that we don't see absolute values this time. And in this case, having absolute values there won't change the correctness of the statement, but it does change the meaning a little bit, right? Having absolute values implies that what's on the inside might be positive or negative, right? And what's on the inside is x minus c. However, because we know that x is always greater than c, we don't have to worry about that because x minus c will always be positive. So we can feel comfortable in changing that from there being absolute values to there being no absolute values. And why don't we put that in our definition? We see that whenever 0 is less than x minus c is less than delta, then f of x would be greater than b. And again, with our quantifiers, for all x such that 0 is less than x minus c is less than delta, then f of x is greater than b. So now let's consider the case where x is approaching c from the left, which I've denoted by having a minus up there. So if x is approaching c from the left, we're restricting our values, right, to be within delta of c, but now x is going to be less than c. So we see that we're only concerned about values in this region. And what's another way to describe this region? Well, we can say c minus delta is less than x, which is less than c. Now again, we can do some algebraic manipulation. We can subtract c on both sides. So we get that negative delta is less than x minus c, which is less than 0. And there you have it. That's what a range is. So we can write this back in. And we can write it in here with quantifiers, again for all x, where negative delta is less than x minus c, which is less than 0, that it will meet our condition. And so again, the difference with this one is that we're looking at values of x minus c that are negative, but still within delta. So the magnitude will be less than delta, and we see that it'll be farther to the right than negative delta, or that x will be farther to the right than c minus delta on our x-axis. So there you have it. These are definitions of thinking about the limit as x approaches a constant and what that means for that limit to equal infinity. Thank you very much for watching.